Hello and welcome to the final lecture in the game science module entitled Particle Systems. You might ask an important question: is the material covered in this lecture included in the in-class tests? And the answer is no, it is not. The tests are actually over, so this material will not be directly assessed. So thank you very much. Don't forget to subscribe my channel and goodbye. That's maybe not that. Actually, if you look into Canvas and Unit 206 particles, you may easily find what fantastic stuff you can do if you master particle systems. I have here a project made in Scratch. Yes, Scratch, that's the programming system created for children to teach them how to program, and I use the principles of particle systems to create this kind of animation of smoke. So if this is what you can do in Scratch, let's have a look what you can do with GFC and the power of C++ programming. So let me download the slides for today's lecture. I started already from the middle. Open PowerPoint, just a moment. We will start in no time. So what exactly particle systems are? This is a technique widely used in 3D graphics programming. Yes, 3D graphics programming. This is where particle systems are first of all used. Today we will create particle systems in a 2D system in a GFC application, a GFC project. Now, what is the goal of particle systems? It is to create a massively animated system. This means that we will independently animate several thousand animated objects on screen at the same time. The method by which we can achieve this goal is to create great number of relatively simple objects. And the benefit, quite obviously, is emergent but complex looking images. What are the particles? There is a number of properties that particles are supposed to hold, to have. It's not a strict definition, so there are particle systems in which the particles don't have all of these individual properties, but usually they will have most of them, or at least a good part of them. So first of all, particles usually don't interact. There are exceptions, but none of these exceptions will be presented today. So particles as a principle don't interact. Particles are not affected by lighting. That's not a big deal for us when we are using relatively simple engine like GFC, but in 3D graphics programming it's quite important that particles are usually not affected by lighting. Particle has a well-defined lifetime, so it will be created at some moment, it will do something, so get through some kind of animation, and then it will end its lifetime, or you may say die. What happens between the birth of the particles and the death of the particle? So within the lifetime of the particle, its motion is ruled by physics, motion or animation. And particles are typically either represented by small points or small sprites. Okay, points are always small, but sprites can be smaller or larger. An example is here. And this is a simulation of a fountain, or if you prefer more formal name for this particular type of system, it's a liquid spray. In the liquid spray, we will animate droplets of water that will all start from a common beginning and they will follow a trajectory like in this animation. What can we say about the particles in this system? First of all, we can formulate so-called initial conditions, so the conditions in which every particle is at the moment it is born or created for the system. First of them, and quite obvious one, is the initial position. As you can see, they are all created at the same place, at the same spot. So the initial position is something that all of them will share. Initial velocity will differ between the particles, not only because some of them are faster, some of them are slower, but first of all, velocity is also the direction of the movement, and this direction is different for different droplets of the spray. Please note that velocity is defined as a three-dimensional vector. So not only x and y coordinates, but also the z coordinate, the depth of the screen. Next thing is the start time. Every particle will be created at some moment, and these moments are different between the particles. And we also have lifetime. Lifetime is how long these particles live in the system. Please note that after the lifetime is over, we can say the particle dies. It's immediately reborn, so we are reusing the particle so that the system displays the same amount, the same number of particles at every moment, including the beginning of the program, when we already start with a number of particles already on screen, even if they were created before the start of the program. It's all mathematically based, so we can easily find the position of every particle, even if the particle comes from the past. Next are the system-wide parameters, so the parameters which apply at all times and at all particles at the same time. So this is first of all gravity, which is universal and will not change and affects every particle at the same way, in the same way, and also time, which changes but also affects all particles the same way all the times. The final thing is what we have to calculate in the runtime, because it cannot be done in any other way, and this is of course the position of every particle at any moment. This formula provides the three-dimensional position. Yes, three-dimensional. This is the vector-based formula, so all these P, V, and G are three-dimensional vectors. T is time, so it's not a vector. And basically how to read this are the position of the particle at the time t is equal to the initial position, so one of the initial conditions, initial position, plus initial velocity multiplied by time, vt, that's a simple calculation of the position in uniform speed motion, and the last part is half of gt squared. G is the gravitational acceleration, t squared is the squared time, so this is nothing else but the formula for the displacement or position in accelerated motion, and in this case this is the gravitationally accelerated motion. Basically that's the formula based on second law of motion and gravity, showing us the position of an object with non-zero initial velocity over the time in the gravitational field, so exactly what we need. Now, to start with the implementation, I will need to sort these parameters into two groups. So the group marked blue are the values that are the same for each particle, like initial position, they all start at the same place. Lifetime, it is 6 seconds for every particle we have, and gravity, which doesn't change also, okay, it's always the same. and the parameters marked red are the values that have to be supplied for each particle. So first of all, these are initial velocity and start time, which are different for each particle and have to be supplied individually. There's also time, not start time, but time, which is not shown in this list, because the time will be provided during the animation. Okay, so having these two groups, so uniform parameters that don't change between the particles, and so-called per particle attributes, so the values that you have to provide individually for each parameter, we can start some C++ definitions. So for the uniform parameters, first of all, let's define lifetime as 6,000 milliseconds. It makes 6 seconds, of course. And the initial position will be defined as three-dimensional vector. Yes, you can easily have three-dimensional vectors in GFC, even if you cannot then show them in 3D space, because GFC is basically a 2D graphics library. But 3D mathematics, no problem. Okay, initial position 400, that's x coordinate, that's mid of the screen. Y coordinate is 50, that's near the bottom of the screen, so exactly where we want this initial position, and the z coordinate 0 can be now ignored, but it is already here. Lifetime, a variable lifetime, is equal to our constant 6,000, so it's an easy part. And gravity, another three-dimensional vector, 0, -20, 0. You might wonder why it's 20, not 10, which is a typical Earth gravitational value, but this is not a Earth-based reality simulation. It's just when I used -10, these droplets of water spray, of liquid spray, seemed too light. Okay, the gravity was not strong enough. With -20 we get a better result, and please note that the x coordinate is 0, z coordinate is 0, and the value of gravity is stored as the coordinate y. Per particle attributes. Here we first of all find the number of particles. We need to understand what the number of particles is, and to find the number of particles we also have to define the period. What is the period? It's the time between creating two consecutive particles. So in this program we will create a new particle every 2 milliseconds, and that's the meaning of this definition here. So every 2 milliseconds we create a particle. This means 500 particles per second, and this means that we will have 3,000 particles per lifetime of a single particle. So during a lifetime of a particle, which is 6 seconds, during this lifetime, with a rate of 500 particles per second, we will have 3,000 different particles created. The particles are reused, so after this 6 second cycle, we will be able to reuse the same particle again, and this means that we will never ever need more than 3,000 particles. They just will be these 3,000 particles will just be injected to the simulation at the pace of 500 per second, or 1 every 2 milliseconds. We'll keep the total number of 3,000 particles, and they will just cyclically go through their trajectory and come back starting from the initial position. So the particle attributes can be provided in the form of arrays of the length of n particles. This define or constant which keeps the number of particles. So the velocity will be represented as an array of 3000, in this case, three-dimensional vectors. Please remember velocity is how fast but also what direction, so it has to be x, y, z coordinates. And start time, which is just the moment measured in milliseconds, so it's a simple array of long integers. Now, having these two arrays, how can we initialize them? Here is the code snippet. We initialize t to 0. T will be time, so that's time of 0, and we have an iteration from 0 to n particles, so this block of code will be repeated 3000 times, once per each of our particles. First, we calculate something that is called lambda and phi. What is that? I will use a geographical metaphor here. We had various sciences in this module, so today it's time for a little bit of geography. Alright, so imagine that our particles are created inside the globe like this, in the center of the globe. Okay, and now what we need to find in order to create the direction vector for the velocity, we have to find random points on the surface of this sphere. The first thing that we can find is so-called longitude, or the Greek letter lambda. Lambda is an angle. Let's imagine that this is that the Greenwich is somewhere here. That's the longitude of 0, and now to find a random longitude, so random position in terms of east or west on the globe, we just need to find a random angle from 0 all the way around to 360. 0 to 360, a random value, because we are using maths functions in math.h library, which uses radians rather than degrees, so we will be rather looking for a random value in the range between 0 and 2 pi, and this will cover east-west direction. Now, to get a particular location on the Earth, you not only need longitude, you also need latitude, so how far north or south the object is. North and south, for a given longitude, given longitude, let's say this longitude here, it's some point between North Pole and South Pole. Let's say that North Pole will be 0 degrees, South Pole will be 180 degrees, so we need another random value between 0 and 180 degrees, so between 0 and pi radians. Or do we? Actually, if you look at this spray, this spray has all range of longitudes all around, okay, but in terms of latitude, there are some particles going up to the north, okay, so this is the North Pole direction, but from this north 0 direction, it's not all the way down, okay? There is a borderline here, and this borderline is actually 30 degrees away from the 0 position. So for the phi, for the latitude, this is the Greek letter phi, by the way. For the latitude, we are looking for a so-called northern subset, so a random value between 0 and 30 degrees, so it's between 0 and pi over 6 radians. And this is exactly what we have in this code. So lambda is equal to m pi, cast on the float data type, m pi times 2, multiplied by a random value. Please remember that the rand function returns a floating point value. It returns an integer value, an integer between 0 and rand max. Rand max is usually, if I remember well, 32,000 something. So to get a random value between 0 and 1, which may be a nice thing to have if we are thinking about continuous subset of random values, you would want to divide the value of random function rand by randmax. So rand by randmax with proper casting of the integer to float will give you a floating point random value between 0 and 1. This multiplied by m2 and by 2 gives you a random between 0 and 2 pi. And the phi is again a random between 0 and pi over 6. So these are these two directions that we really need. The next thing is a calculation of the direction x, y, z, which can be found from reasonably simple trigonometry, which will not follow in detail. Just trust me, I checked this. These three formulas work fine. So if you know the longitude lambda and the latitude phi, you can find a vector x, y, z by using trigonometrical functions of these two angles. And this is exactly what we have in these three lines of code. The following line finds the speed of the particle. The speed is 150 plus randomized value between 0 and 50. So this will choose a random value between 150 and 2000. So this means that there will be no big differences in the speed, but some small distractions, some small differences, basically a random range from 150 to 200. These are our speed. And the final vector, three-dimensional vector of the velocity for the particle number I is Vx, Vy, Vz. This is how we can easily combine the speed with x, y, z coordinate. Next thing is to find the start time equal to the t value, and the t value will be increased by 2, so every 2 milliseconds we have another particle. Everything discussed so far concerns the initial conditions of the particles. So this is in fact initialization stage of the application. Therefore, in terms of the code, I put this code snippet here in the onStartGame function. The next code snippet is for updating the position of each sprite in each animation frame, so in every moment of the animation. You might think that this kind of update code should be located in the GFC application in onUpdate function, and this would most often be the case, but this is quite an exceptional thing. The update code is, as you can see, located in the onDraw function. Partially that's an optimization, but mostly that's in fact we are using just a single sprite for the entire liquid spray. Yes, a single sprite, which is relocated 3000 times in every frame. So basically how it works, we have this iteration across all 3000 particles. Now, a single individual particle is not represented as a single sprite, it's just represented as a single entry in the start time and initial velocity array. In this iteration, we calculate the current position for the current time for each of the 3000 particles, so we basically generate 3000 different positions, and then we reuse the same sprite to set its position on the screen and draw it. Okay, so the same sprite will be drawn 3000 times in each frame in 3000 different positions, and these positions are calculated here. So first of all, time, that's time is the current time, so the current time of the system minus the start time of the particular um, particle plus its lifetime divided modulo lifetime. The simple trick will create a value of lifetime in the cycle from 0 to 6000, which is the maximum lifetime. Each particle after 6000 milliseconds will reset back to 0. This expression here will be the time calculated provided in milliseconds. By dividing this by 1000 we get the time in seconds, which is SI unit for better for physics. And this line, C vector position, it's the implementation of the position formula. So we have initial position, that's the P0, initial position, that's a three-dimensional vector that we have defined a few slides ago. Then we have V0, that's the initial velocity for this particular particle, so for the current particle, multiplied by time, V0 times t. And eventually we have half of gt squared, gravity times t, so it's gravity multiplied by time squared. You might ask why this 1 over 2 is not represented in my code. The reason for that is simple. I took a value of gravity which was 20 because it looked great. I could choose 40 and divide it here 40 by 2, but the question is why. It's all about using constants. 20 just works fine. And the result looks like this. You can notice that this spray is not exactly uniform. There is a untypically, unusually high density of particles in the direction that, using our geographical metaphor, we could say the straight north, so on this axis here. There is indeed an imperfection of our theoretical model of random points on a sphere, which can be made more uniform by replacing the phi calculation with something like that. Let me not go into too much detail. I provide this link here to an article which discusses random points on a sphere in detail, so everyone interested in this topic can use this article. And here is our fountain with all the trimmings, all the corrections perfectly uniform. The liquid spray is the classical example of a particle system, but it's just one of possible particle systems. Another one may be fire. Fire is quite a different particle system. One of the main differences is that fire has a broader base, so the particles of fire are not all beginning or starting at the same position. So the initial position has to be set separately for each particle, so initial positions are per particle attributes have to be stored in an array of a appropriate size with an entry for each particle. Also, we will be using larger particles, less often generated, so the period of generation will be something much higher than 2 milliseconds, and the gravity force will be weak and acting upwards rather than downwards. Fire is lighter than air, so this is rather buoyancy force than gravity. There is one more difference, and this is the use of sprites instead of points. So each particle of the fire will be represented by not so small sprite. Here you can see the sprites, the particles of water. So this kind of sprite, of course, on a very small scale, can be used to animate a fountain, can animate a liquid spray, but in the middle you have a particle of fire, and here is the particle of smoke. The result is like this. Maybe not that naturally and realistically looking, but please remember this is just a 2D simulation. I think that smoke is much better looking in GFC simulation. Smoke is a system that is quite similar to the liquid spray again. So we have all the particles starting from the same point. These particles are large and well overlapping to create a kind of a blob structure. We gravity against is forcing everything upwards. Smoke is again lighter than air, so this is buoyancy rather. And for better results, you can dynamically change the size of the particles from 50 to 200. This is nearly all I have prepared for you today in this lecture. I will just add that particle systems can be used to visualize other effects such as splashes, foams, wave crests, explosions, fireworks, and also rain and snow. The fireworks are actually one of the two final examples of particle systems, and I thought that they are quite appropriate for the final lecture in the game science module. The complete source code of all sample software presented today can be found in Canvas Game Science homepage. Access project folders, which redirects us to a box folder, and the source code is here. Particles fountain, that's the classical example, smoke, fire, and fireworks. I would like to show you something in the fireworks game. This sample provides an easy-to-use sprite explosion class, which looks like this, and this class can be easily reused, not necessarily for explosions. Here's an example. This is Skulls and Ropes game in its final form, so as this is a part of your assignment, sorry, this source code is not to be published. And here there is a sprite explosion object created. The meaning of these parameters is position of the player. 40, that's the speed of the particles, 90 is the maximum angle at which the particles are shot, 359 is the hue or the color, which corresponds to red, 1.0 is brightness, 0.025 this parameter describes the pace of fading from the maximum brightness to complete darkness. And the result is a well-known platform game. Let me go here and here. Whoops, I died. I died again. Okay, so you can see that in this case the particle system is used to provide a splash, a bloody splash here. So that's the final example in this lecture. With this, I thank you very much for your attention, and goodbye.